Our next presenter is Lucie Kafkova, whose title of her dissertation is Figuring Out African Trypanosomes, One Protein at a Time. Her faculty advisor is Laurie Reed in the Department of Microbiology and Immunology. And some of her things that she'd like us to know is she owns a sugar glider. And quite frankly, I had no idea what a sugar glider was until I looked it up, and I'm not going to tell you unless you may already know. She loves magic, dragons, and heroes. So, ready, set, pitch.
In a world where everybody asks, where is the profit? Basic science works with a slightly different equation. You put the money in, and what comes out is knowledge. Basic science is driven by human curiosity, and I am very curious about molecular biology of African trypanosomes. Trypanosomes are single-celled parasites that live in human blood and cause the sleeping sickness. Don't worry, you do not have it. Unless you went to Africa, got bitten by a really big ugly fly, and now you're often feeling like you have a bad flu. In that case, you should get yourself checked. The disease is deadly and not treatable when caught too late. I know molecular biology can sound intimidating, so let's make it more fun. Let's imagine the trypanosome as a Rube Goldberg machine. The receptor on the surface picks up an input, sends a signal into the cell. The signal then travels through a protein cascade until ultimately causing a certain outcome that will be helpful for the trypanosome to deal with whatever the input meant. Except it is not quite this simple. Trypanosomes contain over 10,000 unique proteins that participate in thousands of very intertwined pathways like this one. My task is to find out as much as I can about a protein that modifies the shape and therefore function of hundreds of other proteins. So how do we do that? Well, my favorite way to start is to create a trypanosome that cannot make said protein, and then look for what breaks. Did it stop moving? Is the metabolism broken? Can it divide? Then we can also lyse the cell, causing the whole machinery to spill out, isolate our protein of interest, and look for what sticks to it. Once we think we know what's going on, we can make the proteins, put them in a test tube, and try to replicate simple events that take place in the cell. By these and other methods, I have discovered that my protein of interest, actually, in order to do what it's supposed to, has to be in a complex with very similar but slightly broken protein. This was very surprising because in humans and other organisms, this class of proteins tends to work as a unit of two identical units. So I'm very curious about how this novel arrangement is going to prove advantageous to the trypanosomes or what's going to happen next. Anyway, why am I doing this? Is it really worth spending several years of my life to find the function of a single protein in an odd parasite? I think so. We are uncovering the secrets of life one puzzle piece at a time, and often the pieces that go together come from very unexpected sources. We never know what's going to prove very crucial in the end. And therefore, we need to keep trying to find everything we can. Thank you.
Thank you, Lucie.